All right, we're here. Hang on, we got one question from Ryan, real quick. This is Unit 6 stuff, but that's okay. What's up? No, the answer choices for those are down there, are just for those. These are just to these. Yep. All right, sorry about that. Ryan is getting ready to get finished with Unit 6 and jumping on all over Unit 7 here. We are now in Unit 8, talking a little bit about motion. I got Harrison here to help me out. He's going to be answering some questions while I just kind of sit and walk us through there. So, Harrison, first thing that we need to be able to kind of describe is the difference between scalar and vector quantities. Do you remember what scalar or vector means?
Scalar is only magnitude.
All right, so scalar is only magnitude. Why am I misspelling that one? Sorry about that. What if I gave you, there it is. So the difference between the two is vector quantities are not only the magnitude, the how much, how far, how fast, how long kind of stuff, but it's also the direction. Where scalar is just kind of the how question. How fast was it going? How far did it go? How long did it take? Those kinds of things. So you have scalar quantities.
How and why.
Scalars are the how and where. So scalar is the how, vector is the how, and the where, which direction. So an example of a scalar quantity would be Harrison ran 10 miles per hour. That's great. We know how fast he ran, but it didn't tell us. It might be possible for you, but it doesn't tell us where he was running to. But now if I said Harrison ran 10 miles per hour south, I know which direction he's running. It gives me a little bit better insight to what is going on. So what are some examples of scalar quantities?
Miles per hour, centimeters per hour.
So if we're just talking about meters per second, miles per hour, if we're talking about any of those, so those are all talking about speed. So speed is an example of a scalar quantity. Time, distance, all of those are examples of scalar quantities because they just tell us the how. They don't tell us the direction behind there. Once we get over to
miles per hour north.
So miles per hour north, or maybe meters per second south. All of those now have both direction and, so those are now called, velocity. So the main difference between speed and velocity, velocity is a vector quantity. It's the y and the direction. And then the scalar quantity is speed. So if you think of vector, velocity, speed, scalar. That's one way to remember that. Also inside of here we have acceleration, because acceleration is really just the change in your velocity. How fast did your velocity change? So that's kind of just getting us set up. Scalar is the how, vector is the how, and where are you going kind of situation. All right, so one of the two that we need to talk about is what is the difference between distance and displacement. They're both pretty similar, but one is a vector and one is a scalar quantity.
Distance is how far you're going.
So that would be vector or scalar if we're talking about just how far I'm going. So distance is scalar. It just tells me how far I went. Displacement is going to be vector because I want to know how far, and I also want to know what direction did I actually travel. So there's a couple of ways that we can find it.
Distance is just I went 27 meters.
So distance could be I just went 27 meters.
Displacement is I went 10 minutes up. 10 minutes, 10 meters left, and 10 meters down.
So displacement could be I went 10 meters up, I went 10 meters left, and then 10 meters down. And again, every time I have that direction in there.
That would be the total distance, which is 30.
So the total distance for this would be 30, but we got to talk about displacement, because displacement is not your total distance. Your displacement is how far are you from your beginning. So if we went 10 up, 10 over, 10 down, what is...
It would only take 10 to get back.
It would only take 10 to get back to there. So my displacement is 10 meters, but it's 10 meters to the left because that's the direction I'm away from my starting point. So I'm 10 meters to the left is my displacement. My total distance is 30 because I went all the way around. All right, and you'll need to make...
Finding the shortest possible point from A to B.
It's finding the shortest possible point from A to B, or what we really need to say,
Start time.
from start to end. Where am I compared to where I began from? All right, so there are a couple other mathematical ways that we can do this. If we know that we are traveling in a north, south, east, west direction, so I start off at A, and let's just say I went 10 meters to the east to get over here to B, and then I went 5 meters north to get up here to C. Can I solve for my displacement, which is the distance from A to C, because that was my starting and my finishing point? Can I solve for that? Harrison, do you think we can solve for this?
Yeah.
Yes, we can. If we use a mathematical equation that is simply A squared plus B squared equals C squared. What, do you know what theorem that is? Pythagorean theorem. So because we have a right triangle, and because the directions always travel at right angles to each other, anytime we start talking about north, south, east, west, we can use Pythagorean theorem to help us solve for this. So this is literally talking about 10 squared plus 5 squared. That gives us our C squared. So 10 squared is 100. 5 squared is 25. So C squared is 125. If I just want to know what C is, what function do I have to use now? C is now the square root of 125. And whatever that happens to come out to be. It's going to be 11 point something-ish. Because 11 squared is 121, right? So it's a little bit over 11 point something for that. So again, when we're talking about distance, we're just talking about the how far did we go. That is the total trip that we take. Displacement, we're talking about how far am I from the start to the end. And from there, we may have to do some mathematical calculations if we're talking about, see, refresh yourself. I like that. All right, so there we go. Now we have vectors, displacement. The other thing that we need to take a look at, and I need to throw this in there, I need a new sheet in here. Let's just say, Harrison, I start at A. I go 5 meters to B, and then I go 2 meters to C. What's my total distance that I traveled? Total distance is going to be 7 meters. What is my displacement? How far am I away from the start? It is 7 meters as well. So when it's all in the same direction. So when we're in the same direction, we just add those up to get that. All right? What happens if I traveled out 5 meters again to B, but this time I traveled back 2 meters to C? The total distance would be what? What's the total that I walked? I went 5 and then 2, so the total would still be 7, but now this time my displacement has changed because I've come back closer to my starting point. I'm only 3 meters away from my starting point. So sometimes distance and displacement are equal. Sometimes they are different depending on how we walk. Harrison, can I get a situation where my displacement is 0? How? Harrison said yes.
If you walk back, if you go 10.
Now what do I have to do?
And then you go back 10.
And then if I come back 10, I'm right where I started, right? So my distance, yeah, close, yeah. So my total distance would be 20 meters because I walked out 10 and came back 10, but my displacement now is really 0 meters.
Negative, though.
Can it be negative?
Is that a question? Yes. If you go far. Oh, no, it can't
It's not going to be negative because even if I went a little bit farther, let's say even by 1 meter, my displacement is now 1 meter, so I'm a little bit off. So we can have 0, we can have smaller than, or we can have equal to. Can I ever have it bigger? My displacement, can it ever be bigger than the distance I traveled?
No.
And the answer is no, because I'm always going to be a certain amount of distance away from there. So that's a little bit about distance and displacement. A little bit different than what I was expecting, but let's kind of keep rolling here. All right, so let's talk a little bit about speed versus velocity. What's the difference between speed versus velocity? It is scalar. It's just distance divided by time. Velocity but not only is it distance divided by time, I need to know if I'm going north, south, west, east, which direction am I traveling in there, okay? So scalar, vector, there's the major difference between them. We're both using distance, we're both using time, but I have to add in the direction for it to become velocity. All right? Now acceleration is the one.
Starting time. No, the final time versus start minus starting time.
It's the velocities. So final velocity minus our initial velocity, and divide that all over the time. And since we're using velocity, we know this is a vector quantity as well. We have to have the speed and the direction for us to understand that. All right? Good? Not too shabby so far. All right, positive versus negative acceleration. This is the one most people struggle with. So let's just say we have a car that starts out at 10 meters per second, and it accelerates to a rate of 30 meters per second in 5 seconds. So if we set up our equation, hang on, set up our equation. This is our final velocity, because that's how fast we got up to. This is our initial velocity, because this is where I started out. So 30 meters, hang on. All right, so 30 minus 10 meters per second, and that is all over the time that we said it took, which was 5. So Harrison, 30 minus 10 is 20, divided by 4 is, or divided by, sorry, you're right, my bad, divided by 5 is 4. So this is 4 meters per second, and the key here, it's meters per second over seconds, so it actually becomes meters per second squared. So the rate of acceleration is 4 meters per second squared. Now, that's for a car that went from 10 to 30. What happens if a car went from 30 down to 10? So the equation is still set up the same. Final velocity, 10, minus our initial velocity, 30, all over the time that it took. So now it becomes negative 20 over 5, which now the rate becomes not positive. It is negative 4 meters per second, and again, squared. So the only difference between positive and negative acceleration is the negative sign, because it's telling us that we are slowing down. Some people call that deceleration. We don't like to use that word.
Hitting on the brake.
We like to say that it's negative acceleration. So it's slowing itself down. Good? All right, we're down to our last couple here. Holy crud, what's going on, Mr. Arnold? Right? So this is the difference here. If we're talking about distance versus time, we're talking about speed or velocity. If we're talking about speed versus time, we're talking about acceleration. So this here is acceleration. This over here is just velocity or speed, depending on whether we have that direction or not. All right, so knowing we're talking about speed over here, what do we know about A speed versus B speed, just based off of what we see?
B is faster.
B is going to be faster because what do we know about the line?
The slope is
You can say it.
longer.
The slope is higher or
Higher.
steeper, okay? So we know B is faster than A.
But
Go ahead.
B is equivalent to E.
Wow. Equivalent.
No, not
Yeah.
equivalent. Parallel.
It is parallel, which then the rate of speed is going to be equivalent. So you are right there. B and E, since B and E are pretty parallel, we know that they're traveling at the same speed, which is the equivalent. Okay? So you actually had that correct right there. So because lines are parallel, they indicate the same speed. What's the difference between B and E?
B and E. E started higher up.
Started at a different spot, higher up, further ahead, something along those lines. Take a look at C here. What do we know about C?
See, it's not moving at all. It's at a pit stop.
It's at a pit stop. It's in the garage. It's not moving at all because it hasn't changed its position over the entire time. So this is just a car that's sitting there. What do we know about D? D is a funny one. It's going the opposite direction as all of those.
It's in reverse.
It's not in reverse. It started
at the place they were supposed to go and came back for a sample time.
So it started way away from the original spot and it came back to us. So this is one that was at the store and maybe drove back home, or was at school and drove back home, something along those lines. F is interesting. Talk to me about what F did here.
Basically F, the guy in the car was like, hey, I'm going to go to McDonald's. So he drove up, got there, ordered his stuff, and they said, we're busy in the store, but we'll come out and give it to you in your car. So he stayed in his car for, let's say, 20 minutes.
Okay.
Because sometimes there's a lot of people there. And then he stayed there, and that's why he's at a flat rate.
So F decided to drive to McDonald's. As he drove to McDonald's and ordered, they told him that the food was busy and they were going to have to wait, so he pulled off to the side. And now he's sitting here waiting for his food to be delivered to him. So again, he started to drive away. He had some speed, and all of a sudden now he's sitting at a standstill because we got this flat line saying his position has not changed yet. So that's the distance versus time, or position versus time, or speed graphs. Now we have acceleration, which is speed versus time.
Hi, Mr. Arnold's video.
And that is the one and only? Only? Are you the only?
Can I get a sub? What?
Jackson Shock available? Are you the only one?
Yeah, I want to shout out
There's
in
one
the
other
video.
Jackson Shock.
Okay.
Shout
Okay.
out to Carson in the video. He's doing great today. I taught Mr. on the map.
Okay.
Shout out to Carson in the video. He's doing great today. He taught Mr. Arnold math. Are you happy?
Yeah.
Okay. So if we take a look at these lines here, what do we know about A versus B? Just looking at the line.
A is not moving. It's staying at a constant acceleration. He's putting his foot on the gas, but he's not pushing it down. He's not releasing. He's on cruise.
He's on cruise control. So he is traveling basically he's not on cruise control. He's accelerating at a constant rate.
No,
because
but
his
cruise control is at the same speed as the
but cruise control is not the same as accelerating, because when you set the cruise control, it keeps your speed the same, right?
Oh, that would be.
So that is C would be cruise control because the speed never changes. A is accelerating, but it's accelerating at a constant rate, meaning that it's accelerating at the very, very same pace over the entire time. It's not going any faster. It's not going any slower. It's just accelerating at a very constant rate. So this is you putting your foot on the gas pedal and holding that gas pedal slowly down as the time goes. Now, if you take a look at B, B here is we were kind of going slow, and we really hit the accelerator there. And so we're accelerating at a really fast rate. So what is this?
You see a light about to turn red.
Could be a red light just getting ready to turn red, and you hit the gas to get flying through it. So what do we know then about D, and what do we know about E now?
You see a yellow light.
You see a yellow light, so what are you doing?
Slow.
You're applying the brakes, so you're slowing down. So our speed was high, and now we've slowed all the way down. Now, the D is,
You saw a D, or you're like taking your foot off the gas.
it could be taking your foot off the gas. This could be you saw the red light or construction a long time ago, and you're just slowly kind of slowing down. You're not really jumping on the brakes. D or E here is all of a sudden right about here, holy crap, I got to hit the brakes, I got to hit the brakes, I got to hit the brakes, and I jam on the brakes to get my speed to stop as quickly as possible. Hopefully not your favorite animal in the road. So that's the speed versus time graphs and what's going on. A is accelerating at a constant rate. B is accelerating at a not constant rate, meaning that this is you pushing the pedal down harder and harder and faster and faster and faster. C is you're on cruise control because the speed stays the same the entire time. D and E are kind of the same as A and B, just in the negative way. We are slowing down. Alright, so here are the equations. I just want to kind of touch base with you, make sure you know how to use those equations. Again, speed and velocity, same thing here. Our distance is divided by our time. We can cover up and hide those things. If we want to know what distance is, it's speed times the time. If we want to know what time is, it's distance divided by the speed, etc. from there. Acceleration is the final velocity minus the initial velocity divided by how long it took to change those velocities. So that's why it's meters per second over second, which turns out to be meters per second squared.
And we're ending.
And Carson, where's Harrison? Ah, that's 3 times. All right, so I got to make another video with you.
David Keller, just for like the Carson.
All right, this is for Harrison. How many times I called him Carson in this video? I think it was 3.
Yep.
All right, if you got any questions, as always, come talk to me.